Now that we understand chosen plaintext security, let's build encryption schemes that are chosen plaintext secure. And the first such encryption scheme is going to be called cipher block chaining. So here's how cipher block chaining works. Cipher block chaining is a way of using a block cipher to get chosen plaintext security. In particular, we're going to look at a mode called cipher block chaining with a random IV. CBC stands for cipher block chaining. So suppose we have a block cipher, so ED is a block cipher. Now let's define eCBC to be the following encryption scheme. So the encryption algorithm, when it's asked to encrypt a message M, the first thing it's going to do is it's going to choose a random IV that's exactly one block of the block cipher. So IV is one cipher block. So in the case of AES, the IV would be 16 bytes. And then we're going to run through the algorithm here. The IV basically that we chose is going to be XORed into the first plaintext block, and then the result is going to be encrypted using the block cipher and output as the first block of the ciphertext. And now comes the chaining part, where we actually use the first block of the ciphertext to kind of mask the second block of the plaintext. So we XOR the two together, and the encryption of that becomes the second ciphertext block. And so on and so on and so forth. So this is cipher block chaining. You can see that each cipher block is chained and XORed into the next plaintext block. And the final ciphertext is going to be essentially the IV, the initial IV that we chose, along with all the ciphertext blocks. I should say that IV stands for initialization vector. And we're going to be seeing that term used quite a bit every time we need to pick something at random at the beginning of the encryption scheme. Typically, we'll call that an IV for initialization vector. So you notice that the ciphertext is a little bit longer than the plaintext because we had to include this IV in the ciphertext, which basically captures the randomness that was used during encryption. So the first question is, how do we decrypt the result of CBC encryption? And so let me remind you again that if when we encrypt the first message block, we XOR it with the IV, encrypt the result, and that becomes the first ciphertext block. So let me ask you, how would you decrypt that? So given the first ciphertext block, how would you recover the original first plaintext block? So decryption is actually very similar to encryption. Here I wrote down the decryption circuit, and you can see basically it's almost the same thing except the XOR is on the bottom instead of on the top. And again, you realize that essentially we chopped off the IV as part of the decryption process, and we only output the original message back. The IV is dropped by the decryption algorithm. Okay, so the following theorem is going to show that in fact CBC mode encryption with a random IV is in fact semantically secure under a chosen plaintext attack. And so let's state that more precisely. Basically, if we start with a PRP, in other words a pure block cipher E, that's defined over a space X, then we're going to end up with an encryption algorithm eCBC that takes messages of length L and outputs ciphertext of length L plus 1. And then suppose we have an adversary that makes Q chosen plaintext queries. Then we can state the following security fact, that for every such adversary that's attacking eCBC, there exists an adversary that's attacking the PRP, the block cipher, with the following relation between the two algorithms. In other words, the advantage of algorithm A against the encryption scheme is less than the advantage of algorithm B against the original PRP, plus some noise term. So let me interpret this theorem for you as usual. So what this means is that essentially, since E is a secure PRP, this quantity here is negligible. And our goal is to say that adversary's A's advantage is also negligible. However, here we're prevented from saying that because we got this extra error term. This is often called an error term. And to argue that CBC is secure, we have to make sure the error term is also negligible. Because if both of these terms on the right are negligible, their sum is negligible, and therefore the advantage of A against eCBC would also be negligible. So this says that in fact, for eCBC to be secure, it had better be the case that Q squared L squared is much, much, much smaller than the value X. So let me remind you what Q and L are. So L is simply the length of the messages that we're encrypting. Okay, so L could be like, say, 1,000, which would mean that we're encrypting messages that are at most 1,000 AES blocks. Q is the number of ciphertexts that the adversary gets to see under the CPA attack. But in real life, what Q is basically the number of times that we've used the key K to encrypt messages. In other words, if we use a particular AES key to encrypt 100 messages, Q would be 100. It's because the adversary would then see at most 100 messages encrypted under this key K. Okay, so let's see what this means in the real world. So here I rewrote the error bounds from the theorem. And just to remind you, Q is the number of messages encrypted with K, and L is the length of the messages. And so suppose we want the adversary's advantage to be less than 1 over 2 to the 32. This means that the error term had better be less than 1 over 2 to the 32. Okay, so let's look at AES and see what this means. For AES of course uses 128-bit blocks. So X is going to be 2 to the 128. The size of X is 2 to the 128. And if you plug this into the expression, you see that basically the product Q times L had better be less than 2 to the 48. This means that after we use a particular key to encrypt 2 to the 48 AES block, we have to change the key. Okay, essentially CBC stops being secure after the key is used to encrypt 2 to the 48 different AES blocks. So it's kind of nice that the security theorem tells you exactly how long the key can be used and then how frequently essentially you have to replace the key. Now interestingly, if you apply the same analysis to DES actually has a much shorter block, namely only 64 bits. You see the key has to be changed much more frequently, namely after every 65,000 DES blocks, essentially you need to generate a new key. So this is one of the reasons why AES has a larger block size, so that in fact modes like CBC would be more secure and one can use the key for a longer period of time before having to replace it. What this means is after you encrypt 2 to the 16 blocks, each block of course is 8 bytes, so after you encrypt about half a megabyte of data, you would have to change the DES key, which is actually quite low. And you notice with AES you can encrypt quite a bit more data before you have to change the key. So I want to warn you about a very common mistake that people have made when using CBC with a random IV. And that is that the minute that the attacker can predict the IV that you're going to be using for encrypting a particular message, the cipher, this eCBC, is no longer CPA secure. So when using CBC with a random IV like we just shown, it's crucial that the IV is not predictable. But let's see an attack. So suppose it so happens that given the encryption of a particular message, the attacker can actually predict the IV that will be used for the next message. Well, let's show that in fact the resulting system is not CPA secure. So the first thing the adversary is going to do is he's going to ask for the encryption of a 1-block message. And in particular, that 1 block is going to be 0. So what the adversary gets back is the encryption of 1 block, which namely is the encryption of the message, namely 0, XOR the IV. Okay, and of course the adversary also gets the IV. Okay, so now the adversary by assumption can predict the IV that's going to be used for the next encryption. Okay, so let's say that IV is called, well, IV. So next the adversary is going to issue his semantic security challenge, and the message M0 is going to be the predicted IV XOR IV1, which was used in the encryption of C1. And then the message M1 is just going to be some other message. It doesn't really matter what it is. So now let's see what happens when the adversary receives the resulting semantic security challenge. Well, he's going to get the encryption of M0 or the encryption of M1. So when the adversary receives the encryption of M0, tell me what is the actual plaintext that's encrypted in the ciphertext C? Well, so the answer is that what's actually encrypted is the message, which is IV XOR IV1, XOR the IV that's used to encrypt that message, which happens to be IV, and this of course is IV1. So when the adversary receives the encryption of M0, he's actually receiving the block cipher encryption of IV1. And lo and behold, you notice that he already has that value from his chosen plaintext query. And then when he's receiving the encryption of the message M1, he just receives a normal CBC encryption of the message M1. So you realize that now he has a simple way of breaking the scheme. Namely, what he'll do is he'll say, he's going to ask, is the second block of the ciphertext C equal to the value that I received in my CPA query? If so, I'll say that I received the encryption of M0. Otherwise, I'll say that I received the encryption of M1. So really, his test is C1, he refers to the second block of C, and C11 refers to the second block of C1. If the two are equal, he says 0, and otherwise he says 1. So the advantage of this adversary is going to be 1, and as a result, he completely breaks CPA security of this CBC encryption. So the lesson here is, if the IV is predictable, then in fact there is no CPA security. And unfortunately, this is actually a very common mistake in practice. In particular, even in SSL protocol in TLS 1.1, it turns out that the IV for record number I is in fact the last ciphertext block of record number I-1. That means that exactly given the encryption of record number I-1, the adversary knows exactly what IV is going to be used for record number I. Very recently, just last summer, this was actually converted into a pretty devastating attack on SSL. We'll describe that attack when we talk about SSL in more detail, but for now I wanted to make sure you understand that when you use CBC encryption, it's absolutely crucial that the IV be random. Okay, so now I'm going to show you the nonce-based version of CBC encryption. So in this mode, the IV is replaced by a non-random but unique nonce. For example, the numbers 1, 2, 3, 4, 5 could all be used as a nonce. And now the appeal of this mode is that if the recipient actually knows what the nonce is supposed to be, then there's no reason to include the nonce in the ciphertext. In which case, the ciphertext is exactly the same length as the plaintext. Unlike CBC with a random IV, where we had to expand the ciphertext to include the IV, here, if the nonce is already known to the recipient, there's no reason to include it in the ciphertext, and the ciphertext is exactly the same length as the plaintext. So it's perfectly fine to use a non-random but unique nonce. However, it's absolutely crucial to know that if you do this, there's one more step that you have to do before you use the nonce in the CBC chain. In particular, in this mode now we're going to be using two independent keys, K and K1. The key K is, as before, going to be used to encrypt the individual message blocks. However, this key K1 is going to be used to encrypt the non-random but unique nonce, so that the output is going to be a random IV, which is then used in the CBC chain. So this extra step here of encrypting the nonce with the key K1 is absolutely crucial. Without it, CBC mode encryption would not be secure. In particular, if you just directly use the nonce, feed that into CBC encryption, in other words, you use the nonce as the IV, then we already know that a non-random nonce would not be CPA secure. We saw that on the previous slide. But in fact, even if you set K to be equal to K1, in other words, you just encrypt the nonce using the key K, that also, is not going to be CPA secure and can lead to significant attacks. So I want to make sure you understand that if the nonce in CBC mode encryption is not random, this extra encryption step has to take place. And, so I'll make this extra step kind of dance here just to make sure you never forget to put it in. And I'll tell you that this is an extremely common mistake in practice. There are many real-world products and crypto libraries that actually forget to encrypt the non-random nonce before using it in the CBC chain, and that actually leads to practical and significant attacks. For example, this was not done in TLS. TLS, as we said, used predictable IVs, and that led to a significant attack on TLS. Moreover, the reason this is so important to know is that in fact many crypto APIs are set up to almost deliberately mislead the user into using CBC incorrectly. So let's look at how CBC is implemented inside of OpenSSL. So here are the arguments to the function. Basically, this is the plaintext. This is the place where the ciphertext will get written to. This is the length of the plaintext. This is the AES key. Finally, there's an argument here that says whether you're encrypting or decrypting. And the most important parameter that I wanted to point out here is the actual IV. And unfortunately, the user is asked to supply this IV, and the function uses the IV directly in the CBC encryption mechanism. It doesn't encrypt the IV before using it. And as a result, if you ever call this function using a non-random IV, the resulting encryption system won't be CPA secure. Okay, so it's very important to know that when calling functions like this CBC encryption in OpenSSL, either supply a truly random IV, or if you want the IV to be a counter, then you have to encrypt the counter using AES before you actually call CBC encrypt. And you have to do that yourself. So again, it's very important that the programmer knows that it needs to be done, otherwise the CBC encryption is insecure. One last technicality about CBC is what to do when the message is not a multiple of the block cipher block length. That is, what do we do if the last message block is shorter than the block length of AES, for example? So the last message block is less than 16 bytes. And the answer is that we add a pad to the last block so that it becomes as long as 16 bytes, as long as the AES block size. And this pad, of course, is going to be removed during encryption. So here's a typical pad. This is the pad that's used in TLS. Basically, if you pad with n bytes, then essentially what you do is you write the number n times. So for example, if you pad with 5 bytes, you pad with the string 55555. So 5 bytes where each byte is the value 5. And the cute thing about this pad is basically when the decryptor receives the message, what he does is he looks at the last byte of the last block. So suppose that value is 5, then he simply removes the last 5 bytes of the message. Now the question is, what do we do if in fact the message is a multiple of 16 bytes? So in fact no pad is needed. If we don't pad at all, then that's a problem, because the decryptor is going to look at the very last byte of the last block, which is now part of the actual message, and he's going to remove that many bytes from the plaintext. So that actually would be a problem. So the solution is, if in fact there is no pad that's needed, nevertheless we still have to add a dummy block. And since we add this dummy block, this would be a block that basically contains 16 bytes, each one containing the number 16. Okay, so we add essentially 16 dummy blocks. The decryptor, when he's decrypting, he looks at the last byte of the last block. He sees that the value is 16, therefore he removes the entire block, and whatever's left is the actual plaintext. So it's a bit unfortunate that in fact, if you're encrypting short messages with CBC, and the messages say happen to be, say, 32 bytes, so they are a multiple of 16 bytes, then you have to add one more block and make all these ciphertexts be 48 bytes, just to accommodate the CBC padding. I should mention that there's a variant of CBC called CBC with ciphertext stealing that actually avoids this problem, but I'm not going to describe that here. If you're interested, you can look that up online. Okay, so that's the end of our discussion of CBC, and in the next segment we'll see how to use counter mode to encrypt multiple messages using a single key.